Hi, everyone, and glad that you joined to this session about the topic of clustering high-dimensional data here in part 6 with the topic of correlation clustering. My name is Daniel Kazempur, and Professor Kröger already introduced me briefly into the first session that I will hold this and also the next week with the focus on correlation clustering. But first things first, let us see where we actually are in our current agenda that we have passed so far in this lecture. So Professor Kröger introduced you to the challenges of high-dimensional data. Further on, he introduced you to feature selection, feature reduction, and also a bit of metric learning. Then we moved into this part of clustering in high-dimensional data, and for that we got introduced in what are the challenges, why should we bother at all in clustering in high-dimensional data. And here we got so far the subspace clustering or axis parallel subspace clustering, projected clustering, and bi-clustering so far, so that we get roughly the picture where we are currently in this context. So the methods that we have so far talked about, so this axis parallel subspace clustering, as the name already tells us, detects clusters which reside in subspaces that are axis parallel. So if you've got on the one axis here to guide you to the left figure, we've got here on the horizontal axis the weight and on the vertical axis the size. Then the clusters that we detect with the so far discussed methods of subspace clustering, axis parallel subspace clustering, will obtain one cluster here, for instance, one one-dimensional cluster, which resides in the domain or in the dimension of size, and another cluster which resides in the domain or in the dimension of weight. So we have one cluster here and one cluster here, for example. Nonetheless, there may be cases where the clusters that we are looking for do not actually reside in subspaces which are axis parallel, which can be nicely mapped either to size or to weight, but in cases where, as you see here on the right-hand side, the clusters are in a subspace which is arbitrarily oriented. So this subspace is no longer caged to the original axis of our data space, but maybe anywhere like here or the red one here. So you may think, okay, great, we have here two different settings. In the one they're axis parallel and the other one they're not. What's so important or interesting about it? Well, for the left-hand side, for the axis parallel case, one implication is that the features are linearly independent, which means that, for instance, here in this cluster, the size is independent of the weight, or this is at least the assumption that comes with the axis parallel part. Like here, with this cluster, we say that the weight is independent of the size that we have. So we have here in the axis parallel case, the assumption of feature independence, while in the arbitrarily oriented span subspaces, we have the assumption that there is a linear feature dependence. So here it means on the right-hand side that the weight is linearly dependent with the size. And indeed, if you think of this cluster here, this green one, as a line on the right-hand side, then it means like you have a linear dependence. So with increasing weight, you've got also, depending on the weight, also an increase of the size. So a take-home message here is that axis parallel subspace clusters capture or have as the underlying assumption feature independence, while on the right-hand side, arbitrary oriented subspace clusters, they assume a so-called feature dependence, or kind of like correlation, as we can see here. However, there is also a more finer differentiation. So it's not that we just say, look, there's a linear correlation and that's it. So we have this one axis, as you see in this figure, where the objects are like correlated, just like the one green or the red cluster that we had on the previous slide. So this axis here, where we see an exhibition of a high variance, this is denoted as the so-called relevant correlation or correlation subspace. And this orthogonal one that we see here, this is known as the relevant subspace, or also in some literature known as relevant cluster space or cluster subspace actually. So a subset of features, as we've stated before, may be correlated. However, groups of similar or dense objects may be identified when they are like projected down to this relevant cluster subspace. So if you're looking for clusters, what you would do, you would take this, the objects along this relevant correlation subspace and press it down to its orthogonal relevant cluster subspace. And so depending on what you're looking, if you say you want to have those axes with the largest variance, then you will choose preferably that one. If you say, but I actually am looking for clusters, then you can simply say, I want to have the orthogonal axis, either one or several, because this is two-dimensional, but think of it, it would be a three-dimensional subspace, a three-dimensional feature space. Then you would have this one, for instance, the correlation subspace, and one, and the second one, two. So two of them, these would be like these two that we have here as our cluster subspace, while this longer one that we have would be the correlation subspace. So just that you have these two terms in the sense of the taxonomy in mind. On the one hand, we have the cluster subspace, which is the orthogonal one. There the objects are dense, packed. And on the other hand, we've got the correlation subspace, which means that the objects exhibit a strong correlation among that subspace. And now consider here the following task. So like, let's say we want to cluster test persons to find groups of individuals that have similar correlation among the concentration of metabolites. So something which is in the process of physiological composition, physiological activities, and they indicate like homogeneous metabolic behavior. So in other terms, we want to detect potential disorders, potential diseases. So a challenge here is different metabolic disorders appear through different correlations of subsets of metabolites. So for instance, we have here concentration of a metabolite 1, and here on this vertical axis, the concentration of a metabolite 2. And what we observe is like, well, there is one subset here where the group of persons exhibit one disorder, and another subset here where they exhibit a second disorder. And we have here this group of healthy people. And at this point, one may be tempted to say, and we can also have a third one, here somebody could say, why not just simply apply feature selection or reduction? The problem is that comes with unsupervised feature selection or feature reduction, for instance, PCA, is that PCA itself is global. So it transforms the original feature space into one single representation. It's like you have data which may be arbitrarily shaped, arbitrarily correlated, locally correlated, and you force it down to one single hyperplane. And this may not actually do just to the whole thing. So we face a local feature relevance or correlation. Here we have a local relevance or feature correlation, here a second one, and here a third one. So some features or combination of them may be relevant for the one cluster, like this red cluster, disorder 1, but may be irrelevant. So this correlation here is completely irrelevant to this correlation or to this disorder here or to this disorder here. Therefore, we need somehow multiple representations of these local correlations, and this is something where we reach our limits with PCA. Or to put it in other terms, As an example, we use feature reduction, PCA, and say, you know what, this data, this metabolite data that we have here, we want to encode it, press it down to a one-dimensional representation before we apply clustering. So what do? We take this whole data set, apply PCA to it, obtain this dashed line as the major principal component, as the first principal component. Then we project all of these objects. So all of these objects are like projected down to that particular line, to this principal component. And then we say, okay, let's do some clustering, like for instance, DB-scan, so density-based. And ouch, you see, this is not something which you are aiming for. So the expected 3 clusters that we had beforehand here, they are completely lost. This information is lost by using first PCA, a global approach, and then applying clustering. And by projecting it down to this principal component, first principal component, we have like one homogeneously dense line or dense area, which is, of course, by DB-scan captured or discovered as one cluster, because DB-scan in this mess will not be able to easily separate it. So we see this approach, first applying PCA, projecting down to first principal component, then applying a clustering algorithm, is a dead end. Is there another way that we can pursue for that? Well, let's try the other way around. Let's say we first cluster the data with DB-scan and we recognize still not what we are looking for in this toy example. Nevertheless, it may get better if we apply PCA to it, to this clustered objects that we have here. And so we take here, determine the first principal component, this dashed line again, and then project them down. And the result, again, you guessed it, it's not what we are looking for. So also here, by taking the other way, first applying clustering and then applying PCA, projecting the objects to principal components, is also dead end. This time, due to the fact that DB-scan is not capable to separate them here and here and here, we have no chance to capture these 3 clusters, including their dependencies, their correlations. So this is obviously a dead end. So for a problem summary, feature relevance and feature correlation, this is what we have been talking beforehand. So usually there are no clusters that reside in a full dimensional space. This is the assumption. So if you have like 300 dimensional data, chances are less likely that all 300 dimensions are somehow involved in the clusters, which means that clusters are often hidden in subspaces, so a subset of features within the data. And as such, only a subset of these features is actually relevant for clustering. So for instance, a group of genes play a common role in a subset of experimental conditions, but may behave completely different in other conditions. The second part that we had here is that local feature relevance or correlation needs to be taken care of. So for each cluster, a different subset of features or a different correlation of features may be relevant. As you have seen in this diseases, disease 1, disease 2, disease 3, they had 3 different orientations or directions of their correlation, and also correlation strength. And as such, we need different subsets or different linear combinations of these features. So as an example, different genes are responsible for different phenotypes. Phenotypes, so what is expressed in the part that is visible. And we may have also overlapping clusters, so clusters may overlap in an object. For example, an object may be clustered differently in varying subspaces. For instance, a gene plays a different functional role depending on the environment. So far, so good. We got the problem summary, but we aren't still that much more clever than before. So we know now, we're aware of the problem. We know that we want to capture these different correlations. We also recognize that PCA as a global method applied is not an option, and also varying with orders like first clustering, then applying PCA is not helping, as well as first applying clustering, then applying PCA. So this is also not going to work. But what is it? how can we approach this issue actually? And this is now a nice spot for a cliffhanger. Thank you for your attention so far, and check out the next video where we are going to reveal the secret that we have here. Thank you for your attention, take care, and bye-bye.